Today we're going to talk about a few more of the phenomena of light. In particular, we're going to talk about refraction and scattering. Refraction essentially is the bending of light. You are probably familiar with this by seeing how a straw seems to bend in the water, even though it is still straight. So what is going on? The light traveling from the straw travels in a straight line towards your eye, but the light traveling through the water at first travels in a straight line. When it reaches the surface, it bends. So whereas it would have taken a straight line to your eye, the bending light makes it look like the straw is bent. An example of this is a fish underwater. When you look at the fish, it appears closer to the surface than it actually is. This is because the light shining off the fish reaches the surface and then bends or refracts. Tracing the light ray back, you see where the fish appears to be, even though it is actually deeper in the water. So why does refraction occur? Light has different speeds in different media. It may be constant in a vacuum, but as it passes through water or air, it changes its speed. Think of the analogy of a lawnmower traveling through a sidewalk and then hitting grass. As the wheel travels, it hits the grass and encounters more resistance. That causes it to slow down on one side before the other side reaches the grass. This turns the lawnmower, thus bending its path. Now, light traveling through a vacuum doesn't meet much resistance, but when it enters an atmosphere or water or glass, there's a lot more atoms which interfere with it, causing it to slow down slightly, thus bending the wave. For most materials, the bending of light is dependent on the color. If we have white light shining on a piece of glass, the colors that pass through it each bend at a different angle. The splitting of white light into its constituent colors through refraction is called dispersion. Sometimes when light shines between two boundaries, if the angle is at a critical angle, the light will hit the surface and reflect off it. This is called total internal reflection and is how fiber optics work. It is another key reason for another phenomenon that you're familiar with. When sunlight strikes a nearly spherical droplet of water, refraction bends the light, dispersion splits it into colors, and then it reflects off the back, comes down, and bends again. So the white sunlight gets bent, reflects, and bends again before you see it, causing you to see a rainbow hovering in the air. Because of the geometry, anyone standing here would see light from different raindrops. Thus, everybody sees their own rainbow. If we have a very smooth surface and we shine light on it, the smoothness of that surface means everything reflects off in an organized manner. This is how a mirror works, or when you see a reflection in a very still pond. But what happens if the surface isn't smooth? Each light ray will strike a different portion of the surface. This means that each one will reflect off at a different angle. We no longer see an organized image and just see the color of the surface. Of course, if something's going to reflect like a mirror, it has to be smooth on the order of hundreds of nanometers, the same wavelength as light. On this scale, most things are not smooth, which is why we don't see too many mirrors occur naturally. Now, scattering can be color dependent, which leads to the age-old question of why is the sky blue? Different colors of light are affected by the composition of our atmosphere. Red light and yellow light tend to travel straighter, whereas the blue end tends to bounce around a lot more. Violet actually bounces and scatters more, but humans have very bad purple vision, which is why the atmosphere seems blue. If we had better violet receptors, the sky would look purple. Because the purple and blue light scatters around a lot more, it bounces and comes to us from all different directions. Thus, the sky looks blue everywhere we look. Of course, later in the day, that blue light's being scattered away from our eyes, but the reds, orange, and yellows can still travel in somewhat of a straight line, though there is an effect of refraction in the atmosphere. What we see here is the setting sun, but because the light is actually being bent, what would have missed our eyes has been bent around the horizons, and we see the sun as if it were touching the horizon, when in truth, the sun is actually down here. It has already set. Another way of thinking it is the red light would travel in this direction, but our atmosphere refracts it, bending it, and we would see it otherwise, making it appear as if the sun is over here. Now, the reason it is red is because the blue end of the spectrum scatters, and the green scatters as well, just not as much, so we don't notice it in the middle of the day. This same phenomena is why a lunar eclipse appears red, because the light is bent around the Earth's atmosphere and then reflects off the moon and comes back to the Earth. Now, you might be thinking that the ocean is blue because of scattering. In truth, it's because red light is absorbed by water easier than blue light. So the deeper you go, the more red light gets absorbed, leaving behind the bluer light. If you go deep enough, even the blue light gets absorbed, and it becomes dark.